So thank you, Elevation, and thank you, Yochai and Avi, for inviting me to give this talk about refactoring education. And I think I'm messing up with the speakers here. Wait a minute. Thank you. All right. And as I was preparing this talk for this event, I realized that I actually want to speak more freely about what I think about when I think about computation and education. And I borrowed this title from a very nice book written by Murakami, what I talk about when I talk about running. And it turns out that Murakami has borrowed this title from another book by Raymond Carver, what we talk about when we talk about love. So, that's yet another example of the copy-paste mentality, which became such a major part of our culture, for better and worse. And so, what do I think about when I think about computers and education? Well, first of all, I think about, all the students that I work with. And I think about how fortunate I am to be able to impact the life of so many young people in Israel and outside of Israel. And I also think about how fortunate I am that I can still do a lot of mountain biking. And as you can see, I became a very popular rider, especially among women, all over the world. So this is a worldwide phenomenon. And more seriously, I decided to prepare a talk that has equal measures of pedagogy and software engineering, which presumably are very different fields, but as you know well, they have lots of common denominators. And I started by simply looking at my own career and my own education that started exactly 40 years ago at the Hebrew University of Jerusalem. Now, this was a very long time ago. This was 9 years before Windows and 8 years before the Apple Mac, 13 years before the World Wide Web, 20 years before Bibi. So, I got to tell you, this was a wonderful period. And this was my personal computer. It was called Control Data 6600. It cost $1 million. And I loved this computer because I knew how to make it sing and dance. It had very simple hardware. The software was minimal. And students back then had a feeling of complete control of the machine, something which is all but lost with modern computers, where you have so many proprietary software layers that separate you from the bare-bone hardware. So you may wonder, how did a computer science program look like 40 years ago? Well, first of all, computer science back then was part of mathematics. So you didn't really get a degree in computer science, you got a degree in mathematics. And so I took many courses in mathematical logic, and I played with Turing machines. I proved Gödel's theorem. We talked a lot about computable functions, and which functions are not computable, and so on. We learned some algorithms. There were not too many algorithms back then. And we learned lots of systems, because we had to do lots of system programming in order to make these computers work. So we wrote compilers and interpreters and parts of operating system libraries and so on. So this part of the CS degree was actually more developed and more popular than it is now, systems. And we learned Pascal, which I loved, and C in assembler, which I adored, and Lisp, which I thought was the most wonderful language I've ever seen. And looking back, I asked myself, what exactly did I take from this program? And I'm reminded by what Albert Einstein said, that education is what remains after you forget everything that you learned in school. So I asked myself, what actually remained? And I realized that 3 things remained. And they are abstraction, elegance, and modularity. And these are the 3 things which still guide me in whatever I do throughout my career. So I'd like to say a few words about these 3 values. Abstraction. I remember very well the first time that I saw this piece of code about 40 years ago. It was written in Lisp, and I rewrote it in Haskell, which is a more modern language. And I knew, obviously, that I could also write this code, using some procedural language. And yet, this code kind of struck me. And I said, gee, no side effects. And this code is so abstract and extensible. I can view it as a design pattern that I can extend it to not only sum up the elements of a list, but also maybe multiply them or apply some function that I want to every element in the list, or append to lists, and so on. And there's no wonder that companies like Wix are rediscovering functional programming, because that's what we do. We do list processing, especially when you deal with HTML documents, XML documents, CSS. It's all lists of lists of lists of lists of elements. So, surprise, surprise, this stuff was invented about 60 years ago, and I played with it as a student about 40 years ago. So the lessons that I took from Lisp is that, first of all, I can think about abstraction and implementation separately. That, these are two separate stories, which was a big revelation to me as a young student. And I also realized that programs are written for people to read and talk about and extend and evaluate. And yes, we also want computers to execute them every once in a while, but it's more important to be able to deliberate the code that we write. And in order to do this, you need good languages. You need good paradigms. You need programs. You need to write code that reads like poetry. And this seemed to me like a very important objective. And I realized that in order to write programs which are extremely abstract and lucid, well, you need very powerful infrastructure. You need compilers that know how to do lazy evaluation and just-in-time compilation and tail recursion and so on. And once you have this powerful infrastructure, well, you can do whatever you want. So, abstract programming on the one hand, and a very powerful infrastructure that supports it behind the scene. I also learned lots of lessons about elegance. And I remember that I was, once again, struck by the beauty of data structures like stack, which were extremely simple but powerful. And when I saw this code that shows you how to implement a stack on any host memory device, I was once again struck by how much expression you can get for such a minimal code. So I realized that elegant programs are powerful programs, and that elegance must be pursued almost at any cost, and that anything that you do must be elegant and beautiful, and that the form of the code that you write is no less important than the function and the efficiency. And I think that you will agree with me that writing good, lucid code is more important than having the code run a few fractions of a second faster. So all these things are things that I discovered in my undergraduate education. Modularity is the last virtue which I think we have a complete consensus about. And I realized that when you tackle a problem, whether it is in mathematics, proving a theorem, or writing a complex program, it always helps to start with a reduced form of this problem, solve the reduced problem first, and then extend it to go back to the original solution. And there are many ways to do it, and all of you guys know it and practice on a daily basis. So I realized that modularity is a lifesaver, and unit testing is a lifesaver. And I realized that if you think and act and plan your work in a modular fashion, then you have a series of small victories, which are very important both from an engineering standpoint and psychologically. Especially if you run a startup, it's very important to have many small victories. So these are the things that remained after I forgot everything else that I learned in school. And I'm very glad to say that everything that I do today is based on these three virtues. And I'd like to illustrate some of the projects that I work on, or I worked on in the last few years, and show you how these things are so central in these projects. So let me start with computer science without computers. And this is a project that I do together with Tim Bell and Benny Shore from Tel Aviv University. And what we do is we teach computational thinking. This is a project which is designed for kids in junior high, Chativat Benaim. So we teach computational thinking, and the best way to teach people to think about computers is to take them away from the computer and away from the keyboard. So we do this by engaging the students in games that are played with cardboard cards and beads and strings and playing outside and doing all sorts of things. So here's an example of one of these activities. We give the students 5 cards with different number of points written on them, and we ask them to represent 5. Okay, well, here's how you can represent 5 with these cards. And here's how you can represent 9. And if you insist, you can also use zeros and ones to represent or to code which cards are turned on and which cards are turned off. And as you play this game, you learn binary representation without ever being instructed about it. It comes sort of as a side effect of playing this game. And then, in the course of playing the game, we start to ask the students all sorts of interesting questions. For example, what is the largest number that can be represented? Well, it turns out that, if you count all the points and sum them up, 31. What is the smallest number that can be represented? Well, first of all, the first students say 1, and they don't realize, or some of them do, that you can also represent 0 if you turn off all the classes, all the cards. So the next question is, can we represent any number between 0 and 31? The answer is yes, but can you prove it somehow? I don't request a formal proof, but show me how you can actually come to this conclusion. And is the representation unique? And the answer is yes. There's only one way, one set of cards, one configuration that can represent any number in this range. But once again, can you prove it for me? And then we engage the students in all sorts of tests. Can you describe a method to tell if a number is odd or even? Can you describe a method, if you had a robot that could perform, a very, very limited set of operations, like going to a card and flipping it and then turning to another card, can you give me a series of commands that will cause this robot to add 1 to a given number? And can you write down these commands for me? Can you do a similar, develop a similar set of commands in order to cause the robot to double a number? So that's what we do. We engage the children in such games, and we ask them a set of questions which was very carefully planned and orchestrated. And you see, these questions turn students into scientists. They will not necessarily turn all of them into scientists, but they learn to think like scientists. And this reminds me of a nice anecdote that I read in the biography of Isidore Rabi, who was a professor at MIT, inventor of the radar back in the 50s and winner of the physics Nobel Prize. And Rabi wrote that my mother made me a scientist without ever intending to. And by the way, we try to turn students into scientists without ever intending to. We never talk too much. We never talk about science. We never talk about what exactly we're doing. We want everything to sort of happen naturally. So how did Rabi's mother did it? Every other mother in Brooklyn would ask her child, what did you learn today in school, or did you learn anything? Well, my mother would ask me, Izzy, did you ask a good question today? And then he concludes that asking good questions, that's what makes you a scientist. So that's what we do in this project. You can look it up after the talk. And what you will find is a collection of games about different topics in computational thinking. And once again, all these games are played using readily available materials that you can find in every home and class, whether it is in Israel or in Africa or whatever. And indeed, this project is now being used in many countries around the world. And by now, we have a nice grant from Google to continue to develop it. So this is computer science without computers. The next project that I want to discuss is Matific. And the key players in Matific, at least in the Israeli operation, are shown here. And because I'm going to shift my attention from pedagogy to software engineering, I have to point out that our king of software engineering is Shmulik London, and he deserves most of the credit to what I'm going to show now. So what do we do in Matific? Well, we develop mini-games and activities that teach early age mathematics. So, for example, at some point, students begin to think about what is the meaning of these strange symbols. It goes like this and this. Well, we have several games that teach the meaning of numbers, and here is one of them. We ask students to create a necklace using 7 beads, and as you see, without talking about it too much, at least without talking about it at all, we provide 2 kinds of beads in order to fulfill this, this task. So, this is one solution. Here's a solution of another child in the class. Here is yet another solution, and yet another solution. And it turns out that there are 128 different ways to create a necklace of 7 beads using 2 types of beads. And so the students learn, without ever saying so explicitly, that 7 is 3 plus 4, and 2 plus 5, and 7 plus 0, and 3 plus 1 plus 3, and so on and so forth. So you see, it also takes a mentor to walk them through all these comparisons and discussions. And that's why in Matific, we love multiple correct solutions, because multiple correct solutions provide lots of insight into what it is that you're doing. So you came to my class in order to learn the meaning of number, but you walk out of my class also understanding addition, or at least one interpretation of addition. And you learn this using your own mental devices, at your own pace. And this is extremely important. And one of the most important things in the Matific pedagogy is best described by a quote by Jean Piaget. And Jean Piaget said, whenever we teach children something, we take away forever the thrill of discovering this thing on their own. And you see, nothing beats self-discovery, discovery which comes from within. So in Matific, we never teach anything. We just, we design games, we break our heads on how to design good games, and then we want the children to learn and discover things on their own. So that's what we do. We put together numerous such games. By now, we developed a portfolio of more than 1,500 games that teach mathematics and scientific thinking. And, just like anyone else in this room, we operate under tight deadlines, limited budgets, and very strict requirements, engineering requirements about robustness, because these mini-games are continuously being recombined and repackaged in order to design different products, products that serve different age groups in different schools in different countries. We operate in 45 different countries in 30 different languages. And so, and we run on every, platform that comes to your mind, any web browser and tablet and cell phone out there. And therefore, it has to be done right. And the only way to do it right is to go back to these 3 basic principles of abstraction, elegance, and modularity. And let me illustrate what I'm referring to. Here's yet another mini game in Matific. You have to help these 18 creatures cross the river. So that's how it looks like at the beginning of the crossing. That's how it looks like during the crossing. And that's how it looks like at the end of the crossing. So as you play this game, at some point you begin to discover that there's some relationship between the number 18, 3, and 6. You learn something about the relationship between the number of seats of the boats and the number of trips that the boats has to perform. And this, of course, is only one instance of this crossing problem. And what drives the show behind the scene is what we call a problem descriptor, which contains what you can think about as the model element in the MVC model that kind of lurks in the background. And we also have a rendering descriptor, which is yet another object that contains specifications on how to place these creatures, in which side of the river, and what to do when you click on one of these creatures, and what should the boat do when you click the boat. All these things are defined in this renderer descriptor. So if you take these two descriptor objects and you add to it some graphical elements, what you get is everything that you need in order to render this game. Obviously, it takes some very clever infrastructure to put all this stuff together, and that's what we developed in Matific. And here's another instance of the same problem. Now we learn how to divide 10 by 5, and then we learn how to divide 12 by 2. Once again, the words like division, learning are never mentioned. And how do we develop all these games? Well, we use a language which we designed in Matific called Standard Problem Description Language. And in this language, you can define variables. You can define ranges of variables using other variables and constants. You can define relationships, algebraic and geometric relationships between variables. You can set some constraints to make sure that the problems that you generate will be sensible, not too hard, not too easy, that they will be unique, so you won't have repetitions of the same problem. You can define what questions you want to ask, what hints you want to give, and when. You can define a placeholder for answers. You can define validation rules. And there are many more things that you can do in SPDL, which I don't have time to discuss. But once you came up with this piece of code, well, this becomes the generator of all our problems. Well, from this code, using some randomization logic, we create these problem and rendering objects, which then end up creating the games that the child ends up playing. So this is, an example of, how far you can take functional programming. And look at this other game that you see here. In this game, we deal with explicit division problems. This is something the child will start playing, maybe a week or two later. And if the child can solve this problem directly, fine. But typically, children, have to play with these fruits and distribute them evenly among the 3 monsters in order to carry out the division. And what is striking about this is that, the 2 games are kind of isomorphic. It's the same game mathematically. And indeed, what you can do is take this code that you see here and refactor it and make it more general so that it can support any division problem in this family of games. And then you get this wonderful setup in which you have different episodes, different user experiences, and exactly the same code. The only thing which is different from these 2 episodes are the graphical treatment and the UX. Everything else, all the underlying logic is the same. Here's another example of this principle in action. This is a complete the pattern kind of activity. Here are some missing decorations, and the student is asked to complete them using the bank of decorations that you see here. So here's one way to describe what is going on. We give numbers to each one of these decorations. So and the missing decorations are surrounded in parentheses. We can take this one abstraction layer upward and describe a pattern game in which any 2 decorations can be used, not necessarily 5 and 2. And so suppose that our contents department comes to us and says, well, according to the math curriculum of Australia, we have to come up with several pattern completion problems, so please give us this recipe of problems. Well, how do we do it? Well, we go back to SPDL. And we begin with a demo problem, which has a fixed set of decorations. And teachers always need this because, if they want to demonstrate this problem in front of the students, they don't want any random values popping up. So you need to have always a demo problem. And then here are 3 instances, random instances of simple problems in which we use this particular pattern here, where we don't see this on the LED, ABC, ABC, and the missing triplet ABC. And then we go on to define some harder problems. So here are 2 instances of a harder problem, and here are 2 additional instances of a harder problem, and that's it. That's what you have to define as a programmer in order to make this game happen. Of course, you need the art, but once you have the art in this problem generation logic, that's all that you have to do, except for some very little tweaking, which is always required. And once again, you get this lovely benefit that the same code serves many different games. Here's another pattern matching game in which a train kind of flies into the scene. It is missing some cars, and the child has to complete the cars. It's a different game, different user experience, exactly the same code. So, I have to give you, I think, a little bit of historical context to explain where all these things come from. So this company started about 3 or 4 years ago, and this is a screenshot of our first product. And when we started up this company, we had to bootstrap this company somehow. So I was back then on sabbatical in America, and I went to Boston, and I presented our ideas of pedagogy, early age mathematics to Pearson, which was, still is, the largest textbook publisher in the world. And they were very excited about what I showed them. But I didn't tell them that I had nothing more than a fancy PowerPoint presentation. And so they gave us a nice pile of money, about $500,000, and they said we want 120 such games in 8 months. So, I went back to Israel, I met my partners, and I said, guess what? We have to build a damn thing. We have 8 months to do it, and we have nothing. How should we do it? Well, the situation reminded me of a very nice quote by Abraham Lincoln, who was both a sophisticated and a very practical person. And Lincoln said, if you give me an hour to cut a tree, I will spend 55 minutes grinding the axe. And that's exactly what we did. We decided to take this money that we got and invest most of the money not on developing games, but rather on developing the infrastructure and the architecture and the abstractions that will allow us to press the button and generate many games almost semi-automatically. And that's what we did. We came up with SPDL. We came up with many more such languages and abstractions. And if you look at this code, you realize that the basic idea was to push as much semantics as you can outside the code proper, and to use declarative, functional languages that we can make up as needed, domain languages that will serve our needs, and languages that can be extended, languages that can adapt themselves to students who are slower or faster, so that we can run all the logic of how to give hints and which episodes to give to which children outside the code, outside the code proper. And this code is so self-explanatory that we can actually use domain experts like math teachers and educators to write this code, or to write something which is very similar to this code. So the end users can work with our developers to actually define exactly what they want from these games. So if you want to look it up and play with it, or have your children play with it, you can type Eseretz Baot, which is the name of this brand in Israel, and I think you're going to enjoy it. The last project that I want to discuss is called NAND to Tetris. And this is something that I work on together with Noam Nissan from Hebrew University. And in NAND to Tetris, how many people took this course? Wow, quite a few. It's a course in which we walk into the class and tell the students at the beginning of the semester, God gave us NAND, okay? And this is, the most, sort of the simplest logic gate that you can think about. And what we're going to do during this semester is we're going to use this very humble beginning, and we're going to design a computer, a general-purpose, modern, von Neumann architecture that can execute any program that comes to your mind, including, of course, NAND to Tetris. So in some universities, they do it in 1 semester. In others, they do it in 2 semesters. It became a terribly popular course, which is taught now in more than 100 universities around the world. And so how do we do it? Well, once again, we tell the students that every software product or game, begins with some fantasies, with some thoughts of a programmer or an entrepreneur that has, some idea of a game in his or her mind. So this is sort of the highest form of systems intelligence that you can think of. And then the lowest form of intelligence is what the machine can do, which is basically manipulate 2 symbols. And that's what you have. You have to somehow implement your lofty, abstract thoughts on this bare-bone machine. And closing the gap between this high level and low level is what applied computer science is all about. And that's what we do in this course. We develop the hardware platform and the software hierarchy that enables you to close this gap. So we start with NAND. We abstract away the architecture, and we start with NAND. And then we use NAND to build a set of elementary logic gates, and then we build more complex chip functionality, and then we put together all these chips in order to create a von Neumann architecture. And then we define a symbolic machine language, and we write an assembler that allows you to write symbolic programs in a low-level language. And then we introduce a simple Java-like language, which is called Jack. And we write a compiler for this language. We write a virtual machine for this language, which is very similar to the Java JVM. And voila, you have a computer. And we do this using a sequence of 12 projects, which are completely standalone. So every week, the students carry out one of these projects. And let me illustrate to you one of these projects taken from the hardware section of the course. So what you see here is a classical chip called a full adder, which knows how to add up 3 bits and produce the sum bit and a carry bit. And here is how you can describe this bit. You can do it in a language called hardware description language, which Noam and I specified for this course. And what you see here is a definition of the chip interface, or the chip API, if you will. And this is the chip implementation. It turns out that it can be designed using 3 lower-level chips called half-adders. Now, if you take these chips, if you take this HDL, you have to somehow realize it. You have to somehow run it. So you do it using, of course, this hardware description language, test scripts that Noam and I provide to students who take the course, and you also need a hardware simulator, which is a Java program that we wrote. This program allows you to actually run these chips and see how they work using a visual interface. This hardware simulator became extremely popular, and if you go to Google now and you type hardware simulator, a very sort of innocent search term, something like the 10 top hits that you're going to get come from NAND to Tetris courses and tools, which goes to show how widely used this thing is. And so, if you take 16 such full adders and put them together in some clever way, then you get what is known as a 16-bit adder. And once again, you have to specify it in HDL. So this is the interface of the 16-bit adder. Here is the underlying logic, which describes a set of 16 full adders connected to each other. And let us assume that the student has already built all the chips that lie below this definition. So if you expand one of these chips, well, you get this definition. And if you expand this half adder, it turns out that it can be designed from a XOR and an AND gate, wired in a certain way. If you click XOR, well, it turns out you can define XOR using these 3 logic gates. If you click AND, well, AND is not NAND. And if you click NOT, well, NOT can be defined also using NAND. And if you click NAND, well, the buck stops here. because NAND is a primitive gate, and it goes no further. So you get the actual definition of NAND. And of course, in the course, we start with this definition, and we go sort of bottom up. So we do NOT, we build the AND and the XOR and the half adder, the full adder, all the way to the 16-bit adder. And then, we go on. We build an ALU, CPU, RAM, computer. And you can implement, all these HDL programs, either using our hardware simulator, or if you want, you can also commit them to silicon and use some, FPGA board that you can buy for $50 or so, and actually, burn the HDL logic into the silicon, and then you get a computer, which we call HACK. You can connect a keyboard and a screen to this computer and play Tetris or Space Invaders or any other program that comes to your mind. And of course, in order to do this, you have to complete the second part of the course, where we develop all the software stack that enables to do compilation. And we also write an operating system for this machine using the high-level language, Jack. And you need all these things in order to complete the course and actually make the computer sing and dance for you. Just like I did 40 years ago on this $1 million computer back at Hebrew University. And so, once again, this course became very popular. And I teach it now in Coursera. And last time I checked, I'm bragging now, it was the 7th most popular course in Coursera in terms of student ranking. And you can ask yourself, how come this course is so successful? Well, I think it's successful because Noam and I managed to approach a very messy and complex domain, hardware, using extremely abstract, elegant, and modular approach. And people relate to it, and people enjoy working with well-designed systems and well-designed projects and well-designed APIs. So I'm very pleased to say that these things, which I took away from my education 40 years ago, they resonate in and they dominate everything that I do today, as I hope I illustrated in some of these projects here. And I think there's an important lesson here, and the lesson is that with all due respect to Angular 2 and to Polymer and React and so on, there are some absolute values that put you all guys together, okay? Because technologies come and go. This thing is going to remain forever, okay? And it is our job as developers to celebrate these values and to, transfer them from one generation of developers to another. It's our responsibility to make sure that we and the people that work for us will always develop, beautiful code, wonderful, good-looking architectures, that they will spend, more time on design than on the actual coding, and that, this is, once again, the set of values which are worth striving for. And so, going back to my original title, once again, looking back, I realized that I'm not a good example, because I had the great privilege of learning in a great university with wonderful teachers. Two of my teachers got Nobel Prizes. Two of my teachers got the Turing Award. And back then I didn't realize it, but that I had wonderful teachers. Now I do. And most people around the world, have at best mediocre education. So how can you, possibly scale up this great experience? Well, what is needed, obviously, is great software, great content, enabling technologies. So I personally spend a lot of time developing, what I hope is good software and good content in order to, spread out the stuff that I just discussed. And by the way, everything that I do personally is freely available in open source. And I feel, once again, that the professors who taught me were extremely generous. And now it's my turn to share everything that I do. So once again, you can look up things that I mentioned and use it without any commitments. And what is also needed, in addition to all these goodies, are facilitators and mediators, and people who will help other people learn. So obviously we need MOOCs. It becomes sort of an obvious necessity. But it turns out that people don't enjoy, surprise, surprise, people don't enjoy sitting at home or somewhere and staring at the screen. People want to learn together. So even when you create a MOOC, you discover that there are many meetup groups popping up in order to take this MOOC together. And the notion of boot camps, I think, holds a tremendous promise to education. And there's a lot that universities have to learn from people who run boot camps. Universities have to re-engineer education also using ideas that come from boot camps. And in order to run these boot camps, we need mentors. We need people like you. And I think that, in the near future, every one of you guys will become an educator. You will become an educator, either if you will contribute to Stack Overflow, or if you will if you will teach a few hours a week in some boot camp, or if you will help teach in your children's school, every one of you is a potential educator, and you will enjoy doing it tremendously. Now, in closing, I want to mention that Elevation Academy is, of course, a top-notch boot camp, and I was very pleased to hear that Elevation Academy is now opening a new track for people who will come from the peripheria, and doing this outreach and this great social project will bring many people into the high-tech fold. So chapeau for Elevation for doing this, and also chapeau for Elevation for putting together this great conference. And so I wish you very good lectures, and may the force be with you. Thank you.